Hey, Joe, Ed, and Bill.
Yeah, good
Yeah,
morning, or good evening, as the case may be. Yeah, I
Didn't we just
recognize
talk
those
to you
faces
guys?
from your video.
Yeah, just like yesterday.
Bit of deja vu.
Yeah.
Yeah.
I didn't bring my very nice
Okay.
vest, though. I went with the team spirit option.
All right, Joe, why don't you start us off with your question? With any questions you have?
Sure. I'm kind of curious about your payload. That's a nice payload, nice experiment to run. I guess my first question is you describe your model neurovestibular system. How have you validated that model?
Cal, did you want to go?
How have you validated it? How does it? How have you established that it gives similar results to a real inner ear?
Yeah, so that's a really good question. I guess our intention with this payload was to create a functional prototype, almost as a proof of concept for what we're doing. And so the initial goal of it wasn't to completely replicate the material properties and perhaps the spring damper sort of the properties. Long-term goal for this that we're sort of aiming for is to actually create an FEA-based model of this, and then use in-flight data to then validate this model, so that we can use a different set of materials. Perhaps if we use a silicon gel on that, we can then validate that model for that set of materials. So with that certain size, that silicon, and then make some assumptions about how it should behave if we were to then change that for some more accurate properties with the human ear.
Okay.
And then just to add on as well, probably the next experimental step isn't actually on board a rocket. It's Cal mentioned we've just done a presentation on this, so kind of fluently feeling it at the minute. It's to do some human acceleration events on the ground and try and both quantitatively and qualitatively pick up some numbers and qualifications for what disorientation means. Under
sorry, I felt like I was repeating myself there. I've just come from that presentation. So that goal there. That goal there is I guess to I use the word mapping acceleration, perhaps motion conditions to levels of disorientation, with the sort of intention that if we're provided with acceleration or rotation, we can perhaps predict or perhaps track how tourists or astronauts might feel at certain under certain conditions.
Okay.
So,
what? A related question is, if I remember right, you end up ejecting your payload at like 1,500 feet. It seems like for the experiment you're running, just leaving the payload in the rocket for the whole flight would make more sense. Comments?
Yeah. Well, that's interesting you say that. It's a different set of conditions that we would be exposing it to, and it's initially when we sort of worked with this this experiment, we were looking at parabolic flight in particular. So particularly is that sort of seeing tourism opportunities in that, and so we're looking mostly at that microgravity as we sort of approached apogee in that rocket. And it was also a balance as well, because we do want to increase the capabilities of our payloads. And so while we wanted to, increasing that capability of the payload by allowing it to be removed and come down separately. And so that was, while it's not directly tied into the payload experiment itself, it was something that we wanted to develop as a team. But yeah, you are right. It's a different set of conditions. But we were less interested in that parachute descent.
And for a little bit of context as well, the Australian competition at the time, and time has changed, the payload challenge there was, I think one of them was about using a camera for an extended period of time in descent. So that was kind of another capability goal that we were pointing towards before that competition kind of fizzled a little bit, I think.
Oh, I see. Okay.
If I can pop in there. Okay. Under the buckling analysis that was done, the presentation graphs indicated 20 kilonewtons, but the oral portion said 200 kilonewtons as far as when the fuselage buckled. So which is it?
Yep, that's true. So it's supposed to be 20. The recording wasn't able to be edited because I lost my power and I couldn't edit the video again. So in the video, we did do an asterisk and say 20 kilonewton.
Okay.
So sorry for the confusion.
No problem. And if I can jump back to the payload, what type of strain gauge are you using to measure the wire deflection?
Yeah, they're a film strain gauge. I perhaps go by a number of different names, but they're like almost like a they're a film there that gets laid onto that spring steel. We're also experimenting. Those are the sorts of things that you might be placing on other metals elsewhere, and we're looking at putting them on airframes in the future. But there's something that we can just sort of place on with an adhesive.
Ah, okay. Okay, Bill, your turn.
Yeah. Okay. Yeah. One of the, let me just say that I was extremely impressed with your overall presentation, and I just made, just looking back at the comments I made, a lot of very good work, and some, I'm besides being a pilot, and I'm a modeling and simulation guy. So the way you laid out your assumptions, the way you did your sensitivity analysis, your discussion on of your goals, and that were all excellent. I mean, top notch as far as your analysis. So kudos to you guys for doing such a great job. The one thing I was curious about is I noticed you're using some 3D printed components, and specifically using PETG for your filament. And and I know it gets hot in Australia. If we were launching today, it'd be 107 degrees Fahrenheit, so pretty hot. And when I print things out in PETG, if I leave them out in the sun too long, then they deform and lose their shape. So have you tested that resistance to heat, and as far as those particular components?
Yes, we have. So we chose PETG namely because it doesn't warp under heat as much as your classic PLA will.
Yep.
The HDT of
Yep.
PETG is around 70, 80 degrees Celsius. Not sure what that is in Fahrenheit. I think 100 Fahrenheit is roughly 40 degrees.
Yep.
70 degrees Celsius is 160 Fahrenheit.
Okay, thank you. So it's not particularly prone to warping. If we stuck it in an oven situation, which it probably won't be under being encased in the rocket, we don't expect to see any warping. But if we do, we'll just replace the component with fiberglass if we need to.
Yeah. Well, the other thing you can do, don't paint your rocket black. Have it in some kind of light color, which will certainly help. But like for example, I got printed out a bunch of little holders for my sunglasses to put in my car, and after the first day, they were all deformed and fell off because of the, just the solar heat in the car. So that's, something that I've seen happen in real world. And so that's just something you need to keep cognizant of. I've noticed a number of other teams have been using some different filaments. Onyx is sometimes mentioned which is nylon with carbon fiber in it, which is extremely robust. But it's not something that you can print in an ordinary consumer grade 3D printer. But so just consider that as well. But beyond that, the other thing I had a question about is I just couldn't, maybe I'm just being dense here, but I couldn't quite wrap my head around which way your nose cone was going to be oriented when your payload release, right? Your payload's in the nose cone, and then you were going to release it after the nose cone is separated, but from the way it usually is your nose cone is pointed nose down, and so then that would require the payload to exit vertically out the top. So how does that happen?
I can probably take that one. So when we have our drogue deployment at 10,000 feet, the drogue is situated in the bottom part of the rocket. So we have that separation at the bottom part of the rocket. You're right, the nose cone is pointing down as it descends on the drogue. When we do have that nose cone deployment at about 3,000 feet, the nose cone will come straight off, and that's where it exposes the payload bay. The mechanical release is kind of, I'll try and act it out, is holding it up here. And when that mechanical release releases the payload, it will fall under its own weight out from, I guess, the top of the rocket facing towards ground.
Yeah, so actually the payload is connected to the bulkhead, which is contained within the tube that connects to the bulkhead. So to the nose cone. Yeah, the payload hasn't actually connected to the nose cone at all, if that makes sense.
Okay. So I misunderstood that. Yeah. So I kept trying to figure out how that worked, and it just scratching my head. So. Okay.
Yeah, I think we potentially could have had a clearer diagram there in the video, but yeah.
Yeah, that certainly would have at least helped my understanding. Ed, we got a couple minutes left. Ed or Joe, you have any last questions or observations?
First off, I'll comment that I've got stuff I printed in PETG that's been sitting in my truck toolbox for many New Mexico summers, and I haven't had a problem with warping. Okay. I'm curious about your PID motor control on your air brakes. And what I guess I'm looking at those motors and thinking that you're going to have very high accelerations relative to the maximum speed of the motor. So I'm sort of expecting your PID terms to end up looking almost like bang bang control. How's that working out?
Yeah, so an important thing I think that we should recognize about the control system itself is it is very experimental. We do think it will help our competitive goals in achieving 10,000 feet, but especially in the first few test flights of that control system, it's going to be really nailing down those control parameters. So your PID parameters. So it may turn out, it could be a simple proportional system, or as you say, a bang bang system. But again, experimental the first few flights to really nail down how to best implement that control system.
And I would expect that nailing those parameters down, you should be able to do just on the ground. Because you just
potentially. It's also we still need to see how the mechanical system operates under such heavy loading. We can do ground tests. Yeah. And we can do as many simulations as we want, but actually seeing it under, with all these vibrations going on as well in the rocket, is still something which we have to investigate through testing and continuous iteration. I think it was mentioned before, this is still an early iteration of the control system. Yeah. So there's definitely plenty of room for improvement in the software and the mechanical design as well.
Okay. I have to call time and really appreciate you coming. You've done a great job, and good luck. Good luck in the other competition, and we're going to expect to see you next summer in New Mexico.
Absolutely. Thanks, Joe.
Thank you
Thanks,
very
Ed.
much.
And thanks for your
Really
kind words, Bill. Thank you very much. We'll catch you later.
Thank you, guys.
Thank you so much. Thanks.